So, as I said when I introduced the syllabus, we're going to be talking about the firm. And the firm is an important construct in its own right. In economics, it doesn't only show up in microeconomics, there is managerial economics, there is a whole theory of the firm that extends beyond microeconomics, gets into institutional questions, gets into sort of the formation of contracts, the question of why do firms actually exist? Why don't we just contract with each other and don't exist within a structure of a firm? So there's big questions about firms. But what we're going to be doing in this class is discussing the firm from the neoclassical microeconomics perspective. And the neoclassical microeconomics perspective is rather limited, right? It presents the firm as effectively as a production function, right? It presents the technology of the firm as represented by a mathematical function, right? And then on the basis of that mathematical function that describes production, we build all of the sort of the optimization problems that we're going to be building, the profit maximization problem. Again, the other thing that you will notice is that the way that we model firms has a very similar structure to the consumer problem. So let me get started, and I'm going to start with discussing what is the firm's problem in microeconomics. So I'm going to say here the firm's problem. Okay, going beyond sort of this idea of why do we exist, how did we form, what brings everything together, what are the questions that are being asked. So the first question is which combinations of inputs the firm is going to be hiring a variety of inputs to produce output, right? So the first question is which combinations of inputs are going to produce a given level of output? And what are inputs in the production process, typically in economics? Capital and labor, other things? Technology is an input, materials, natural resources, an array of things. We're going to limit it to capital and labor and technology in the beginning, and then all of these models can be expanded to incorporate additional inputs. That is the equivalent of thinking about two goods in the consumer optimization, maximization problem, right? Obviously, you don't have to have two goods, you can have n goods. In the same situation for the firm, you don't only have to have capital and labor, you can have n inputs in the production process. So, which combination of inputs produce a given level of output? Let's see. The second question, before I move on to the second question, why are we thinking about this type of a question? Right, the firm is faced with a particular demand, so it might be considering bringing X units of the good to the market. Right, and for this to be sort of decided, you need to be thinking about, well, if I hire this much of labor and this much of capital, that will allow me to produce X number of units for the good. Okay, that's sort of the consideration here. The second question brings in prices, and I'm going to say that given now input prices, what is the cheapest way to attain a certain output? So this brings in the economic reality, right? In the same way that in consumer theory, you were thinking about, oh, you have preferences over a variety of goods and quantities of goods that I could be consuming, right? I could be equally happy by trading off across different bundles of goods. In this and sort of then getting grounded by reality, you're like, oh, this thing costs this much, this other good costs so much, I have a budget, I need to stay within, I'm staying within a specific sort of level of utility. So here we're bringing in prices of the inputs that the firm hires, because that's sort of how the firm gets grounded to reality. It costs to hire labor, it costs to employ capital, right? That brings you to sort of this question of cost minimization. Okay? You want to produce this much, you have a specific budget, you have to figure out what the cheapest way for producing that is. Sort of thinking rationally. Then the third question, given now output prices, How much output should the firm produce? So now we're bringing in one additional dimension. The thing that you're going to produce with your labor and your capital has a price in the market, right? Given that price, assuming in the beginning we're going to assume that the firm is a price taker, right? So it's going to see out there in the world how much does that particular good gets what's its market price. So given that price that I can sell my good for, how much output should I be producing, right? With the optimal combination of labor and capital, getting you to an optimal output given the output prices. So this is, all of these three have names. So I'm going to then say that one is a question on regarding the firm's technology. So essentially, this is a study of how the firm transforms inputs to outputs. This is an engineering, essentially, question, and we narrow it down to a production function that's going to reveal how that transformation happens. How do you take labor and capital and make it into widgets, whatever it is? The second question is regards the cost minimization. So I'm going to say regarding cost minimization. So it's also referred to as the cost minimization problem. And the third one, you might have guessed it, given the output prices, you decide how much to produce on the basis of a profit maximization, right? So this is regarding the profit maximization problem. So, questions on this one, in the way that we're structuring sort of a discussion of how the firm behaves as a rational agent in microeconomics. Hopefully that makes sense, right? So the topics that we're going to be covering, first of all, we're going to be looking at the firm's technology, right? So I'm going to say topics on technology. We're going to be discussing one, the production function. Let me do something here. See, the second thing that we're going to be discussing, the concept of the marginal product and the average product. So you increase inputs by one input by one unit. What do you get on the margin in terms of output? That's the idea here. The concept of the isoquant, from the Greek iso meaning equal and quant being quantity. So these are curves that represent the technology of the firm as a contour plot. You'll get a sense of that later on. And the MRTX, which is effectively the slope of that curve. So we're going to introduce that a little bit later. Returns to scale, very important topic for understanding the market that you're operating in and for the government to understand whether firms need to be regulated or not. Homogeneous functions and the elasticity of substitution. The idea here being the substitutability across labor and capital. So we do live in an age where we are seeing a lot of substitutability across the different inputs of production. Technologically, there are feasible or unfeasible sort of substitutions, so that the production function is going to tell us what's feasible and what's not feasible. But then eventually the choice of whether that's going to happen will depend on the cost of the production inputs, right? So, for example, minimum wage goes up, people are trying to find ways to substitute away from labor, right? That sort of natural way of thinking for profit maximizing sort of problems. So these are the topics that we're going to start with, because we're going to first explore technology. That's question number one over here. Then we're going to talk about minimization of cost, and then we're going to talk about profit maximization. But we're starting with all of these topics on technology. So let's start with some discussion of this section in microeconomics is called producer theory, in the same way that in the first half of microeconomics you were talking about consumer theory. So here we're in the space of producer theory. So the producer, who is the producer? Here, I would say the second most important or the second important actor in economics, the first being the consumer, right? We were going to call the producer here. Producer is a firm for our analysis. It carries out a production process transforming inputs into outputs. Fantastic. To do this, the firm employs a certain technology, as we're going to call it. I like to call this a recipe as a different way of thinking about this, because in many cases technology shows up inside this recipe. So it's a combination. Sort of the production function involves the technology and the different levels of labor and capital. So if you think about the whole thing as a sort of method for transforming inputs and outputs, it's sort of the better way of conceptualizing that. So employs a specific technology, which we are going to call the production function. And we start with an assumption here that we're thinking about a single product firm, right? The firm that produces one type of a good. And this discussion can be extended to multi-product firms also. So this production function, what does it do? It shows the maximum amount. This is a very important point. It shows the maximum amount of output, and we're going to symbolize output with the letter Q, standing for quantity, right? Lowercase q for the output of a single firm, uppercase Q when we're going to be talking about the market as a whole, right? If there is multiple suppliers, multiple small Qs, all of these small Qs is going to be the output for the market as a whole, right? So yes, so maximum amount of output that can be produced using combinations of inputs. So that can be produced using alternative combinations of inputs. And that could be capital or labor. Now, the production function then is a mathematical construct, right? And that should not scare you at all, because you have already seen a lot of mathematical functions of one arguments, two arguments, n arguments, right? So this is essentially what economists are doing here. So the production function then is a function f that we're going to define as having a domain in the positive Rn space, right? Because it could have n different arguments, labor, capital, natural resources, n number of those types of inputs. All of those things have only positive values, right? You don't have negative labor, you don't have negative capital. That's sort of why we're using that as the domain. And that function, what does it do? Like any other function, it's a mapping. You're mapping from the space of all of these inputs that you're utilizing in the process, mapping those into the space of R, space of real numbers, and the positive real numbers, right? Because that's your output, right? You have a single output. It takes positive values or zero, depending on where you are. If you don't employ any inputs, obviously you're going to have zero output, right? So that's sort of what this function does effectively. Nothing too fancy. So I would say it describes for each vector of inputs. So you're going to have a vector like x1, x2, xn. That's capital labor, natural resources, and so on and so forth. The maximum output, Q, being equal to the f of x that can be produced. So what comes to your mind when I talk about the maximum output, and what would be the alternative? Why would we worry about making sure that we're talking about the maximum output that you can produce with a certain number of inputs?
When you say alternative, it could be the minimum input. That would be the opposite.
So you decide on the amount of output that you want to produce. You are equivalently thinking, what is the minimum amount of inputs that you need to produce that? That would be sort of an equivalent problem. But what does this mean? When we're assuming that there is this firm that is utilizing this production function, what are we assuming effectively about this firm? We're not talking about prices at all at this point. We're not talking about price taking behavior. Prices are not in the picture at this point. What do you think we are talking about when we're saying that this is what we're conceptualizing as a technology? So the answer here is that we're thinking about an efficient firm, right? That it's fully utilizing the amount of inputs that it's employing, right? There is no waste, there is no leakage, there is no paying attention to other things other than producing that amount of output, right? We're going to see that concept, but we're essentially talking about an efficient firm. That's the idea behind this. So that's setting us up for thinking about sort of the math a little bit and the construct that we are developing. So if this function f, which is a production function, right, is differentiable, so what does that mean? It means that we're dealing with smooth functions, right? We're not dealing with functions that have kinks, at least for the points at which they are differentiable, right? We can calculate its partial derivative. It's called the marginal product. That's a very important concept in economics. And it's the marginal product of input I. So generally, we're going to talk about I inputs 1, 2, 3, 4, 5, n. So if you differentiate that f function with respect to one of these xi's, you get what we call the marginal product. So this is denoted as P, marginal product of input I. So I becomes a subscript, and it's a partial derivative, like the ones that you have handled in many situations so far. It's going to be the partial derivative of your f of x. And remember, your f of x, this is a vector, right? That's x1, x2, x3, xn, differentiated with respect to that particular input xi. So what does this really mean? When you change one of your inputs by a little bit, say you add a little bit of labor, you hire some additional labor, what is going to happen to your output? That's your Q, that's your f of x. Yes, as a concept, it makes a lot of sense. And you're controlling everything else. Everything else is constant, right? You keep capital constant, you keep natural resources constant. All of these other x's are held constant. And that's how you measure your marginal product. So that would be the marginal product of labor. So you are going to see, for example, in your texts, something like MP, that would be the marginal product of labor. In neoclassical theory, eventually you'll see we're headed down that way. Each worker is theorized as receiving the value of their marginal product as the wage. That becomes effectively the wage. The value of that, expressed in dollar terms, becomes sort of equivalent to the wage for a worker in the production process. We'll see more of that later on when we start talking about prices in the production process. So this is essentially defined as the rate at which output changes per additional unit of input I. Make sense so far? It is also called a marginal physical product. Physical, because it's measured in the units of the output, right? So let's use a practical example. Let's say you have production function that Q is equal to F, K, comma, L. Yes? Everyone is comfortable with this. Essentially, you have your two inputs, capital and labor, and you have your output. Let's write the marginal product of each of these inputs, right? So if the production function has two arguments, you're going to have two marginal products that you can calculate, the marginal product of labor and the marginal product of capital. So that's going to be del K, right? When you differentiate with respect to capital, we're going to denote that as F, small lowercase k, as a subscript. Is everyone comfortable with that notation? That we're just doing a notation at this point. Also, the marginal product of labor, F del K, should be writing it as lowercase l, is going to be F of subscript L. Note here, all other inputs are constant, which is the idea behind the partial derivative, right? So when you take a partial derivative, everything else is held constant. which is going to be a useful concept for us here. Now, you can go one step further and think about how that marginal product is going to change as you are change the amount of a different input of production. Okay? So here we're going to be heading into the concept of the second partial derivatives. So here's the sort of the technological question. How does then marginal product of an input change with different amounts of the input? We're going to first do that with itself. So, for example, when you're hiring 5 units of labor, you have 5 workers in the firm, and you add a worker, you're going to get a marginal product. You're going to get sort of at 6, the output that you get for the 6th laborer. Is that marginal product different when you had a 6th laborer, an 8th laborer, a 10th laborer, and so on? Okay, that's what we're going to try to capture here. So how do you capture this mathematically? You need to do another level of differentiation, right? So you're going to say, well, now I'm thinking about the change, let's say, in the marginal product of capital as I am going to change capital. So that will be effectively the second partial derivative of this f function. And we're going to symbolize this as f subscript k, because we're taking a partial derivative after we've taken the first partial derivative. Is everyone comfortable with this notation? Okay. And this we expect is going to be less than 0 for high enough level of k, right? Same thing for MPL, right? So del MPL, del L, labor, second partial derivative, symbolized as f subscript LL, also negative for high enough level of L. You understand that this is quite loose as language. What is high enough? But do you have a sense of what we're trying to get to by making this particular assumption about our production functions without changing anything else? Right? Because imagine you are in a. So, what would be the easiest example that someone can think of? Right? You have a pizza. You can create any sort of mental experiment here. It's like you have a pizza shop, and you're adding workers, and the added output of workers once you achieve a high enough level of labor is going to be decreasing. They're going to be on top of each other. Who's going to be doing what in this? And this happens because you're not changing your capital, which is the amount of machinery that you have in the building, right? So if you don't change that at the same time, that's why we're this is assumed in the production process, which hopefully makes sense. You have 5 laptops in here, and you're asking people to do work, and you keep on adding laptop users, and you're not increasing the amount of laptops. It makes intuitive sense, I would suspect, right? But mathematically, this is a second partial derivative, right, that has a specific sign. And we're going to be using those types of things. All right, so everyone is following along. We're good up to this point. Let's see. Now, I started this discussion by saying how much does the marginal product of an input with changes in other inputs, and then I switched to first considering the case of what happens when you're changing the input itself. So now let's get to that other question. So I'm going to say here, how about the impact of changes in other inputs? Of changes, right? So when I'm writing this down, I'm saying, well, what is the impact of changes in capital when we're considering the marginal product of labor? What is the impact of changes in labor when we're considering the marginal product of capital, right? So we're sort of playing with that sort of setting. So I'm going to say, for example, the marginal product of labor as K changes. Okay, assuming that, again, what do we consider a marginal change? For labor, it's easy, right? 1 additional labor hour. You hire 1 worker to work for another hour. Distinct, a small enough chunk. What is a marginal change in capital? Is it a laptop? Is it a piece of machinery? Could we think about this as adding a factory in the production process, right? That's something that we'll be discussing quite a bit, because all of these changes take a certain amount of time to complete, right? Adding a laptop can happen quickly. A big piece of machinery might require an order, a few months. A factory might be a multi-year process, right? So that brings us from the short term to the long term, right? There are some implications there. So what is a marginal change is always a good debate to have in these production processes.
To get a person trained up, or some of those more real world type situations where they might not be as productive.
Right. Yes. So you could definitely take into consideration the amount of time that you'd need to train a worker into the sort of this calculation. You would assume that the marginal product of labor will be counted perhaps differently if you have a worker who is in training versus a worker who is in fully trained and sort of engaged in the production process. I guess you would add them into the production function as a different type of labor. That's what I would do mathematically. If you wanted to build that type of model, there are different types of workers, right? So perhaps that would be the input there. Think about, so there are folks that focus on entrepreneurship. They add managerial skill, for example, or managers as a different type of labor in these production function processes, right? So it's a mathematical function. You can define it any way that you want to define it. And we will see that as progress is made on mathematical modeling of production, either at the level of the firm or a nation as a whole, right? When we talk about economic growth, we talk about these production functions too. And the way that you're going to define them defines the type of a model that you're essentially working with. So think about this then as a different argument in the production function. So let's see. So we're thinking about the marginal product of labor. How does that change as capital change? Can we write that using a mathematical statement? Yeah, of course we can, right? It's a partial derivative of this with respect to this. So let's write this as del of the marginal product of labor, del K. So how do we write this? Del of F, second partial derivative. Well, should I write this? Yes, that's a little bit of an overkill, but in short, when I write those things, I'm going to be going to the notation of the subscripts, right? So I'm going to be writing f of LK. What would you say that this second partial derivative is? And maybe not always, but often. Do you expect the sign of this thing to be in a production process? Let's say you're increasing capital by a little bit. What do you expect is going to be happening in the marginal product of labor? You would expect it to be a positive, right? And this is often the case. So we talked about sort of the marginal products. Now let's move on to these concepts are going to come back as we're analyzing sort of production technology. So we're at the stage of definitions at this point. Let's talk about the other construct that we're going to call the average physical product. So the average product or average physical. That's a simpler than the marginal product, right? Because how do you get average? You divide by a certain number of units. In this case, if we are thinking about the average product for labor, we're going to take the product, Q, and we're going to divide it by the labor. So how many units per worker, generally, right? So, for example, for labor, this is also what people refer to generally as labor productivity, so also known as labor productivity. We're going to write this as AP for average product, subscript L of labor, and that's simply your Q or your F of X, however you want to write this, divided by the units of labor. You're producing 100 units, utilizing 2 laborers, that would be 50. So this can be written as f of k comma L in the case where the firm is producing only 2 units, is producing using 2 inputs. Note here that this also depends on the level of capital, right? So how much capital you are utilizing is going to define how much your average product of labor is going to be. Okay, so let's use these concepts now and put them all together and give a specific functional form that we can work with, right? So the example here, what is a sort of a firm producing, I don't know, mouse traps? They cannot differentiate mouse traps as much. At least there's the snapping kind, the inhumane sort of version, and then there is the things that you trap the thing and you have to take it outside and it survives. I don't know how. I haven't seen other sort of inventive ways. For there might be. We should look at patenting activity. But are the fancier ones more like a hobby, or he's like redneck engineering? That's good too. It's good to think about it that way. So let's say you have that type of an output, f of k comma L, right? So you can assume that you need some amount of labor, some human activity, and some amount of capital to produce those mouse traps. And someone can make a calculation, usually sort of some manufacturing engineer, that can come to you, to an economist, and say, oh, here is the technology, right? This is 600 times k squared times L squared minus k to the power of 3 times L to the power of 3. It's a function that raises the quantities of capital and labor to the power of 2 to the power of 3. And effectively, once you plug in a certain amount of capital and a certain amount of labor, you're going to get your output, right? So in the simplest case, if K is 1 and L is 1, what would you be getting here? 599, right? So it gives you a sense of sort of the production function. The form of this production function aligns with these concepts of what do you expect marginal product of labor to be, what do you expect, how do you expect the marginal product of labor to change as you're changing capital, and so on. So typically you're going to see production functions that align with sort of what we expect to see in the real world. But this is something that can be calculated, right? This is not, it's not like your equivalent of sort of the utility function that is a concept that is latent, that is hidden effectively. This is something that can be measured in a manufacturing process. So if you want to figure out how capital and labor gets transformed, you can ask people to make these types of calculations so that you can utilize them in the production sort of activity. You can use econometrics perhaps to estimate that production function. So, but in our course, we're going to utilize this as a given, and we're going to do an analysis on the basis of the given data. Or as we're moving into more abstract models, those powers might be an alpha or a beta. We don't know exactly how much. It could be 1.5, it could be 2, it could be 3. Whatever it is, we're going to develop a model, and these things are going to be in the model abstractly, and we can have an answer irrespective of what that alpha or beta is. Give me an alpha, I'll give you the sort of the answer. Give me a beta, I'll give you the answer. So that's a very specific example. The first thing that we're going to do is we're going to define the short run. And the short run is typically going to be the situation where capital is fixed. Capital, and because this production function only has 2 arguments, any other input of production that could have been part of the calculation would have been fixed, right? So the only thing that you can change is labor, because it's quick to hire and fire people, and so you make those adjustments. And typically that's what we define the short run in economics. In the long run, you can employ more capital, you can build factories, but again, that there's no specific set time for what is short run, what is long run, right? Long run is all of the inputs of production can be adjusted. Short run, You can only sort of adjust one input in the production process. So if we define the short run and we say capital is fixed, well, it's fixed at a particular level. It could be 100, it could be 1,000, it could be however many units of capital you're employing. So we're going to assume here that capital is fixed at 1, just to make our lives easier. Equals the value of 1. So if that is the case, how can we rewrite this production function? So Q is now going to be equal to an f of 1, comma L. Yes? So this is really an f of L. So what would be the functional form?
600k squared.
Oh, remember K has a value now.
No, I'm sorry. I switched the L. So 600 minus L squared times L.
Minus L to the third, right? So if this becomes 1, 1 to the power of 2 is 1, right? So this is 600 times L squared. Then minus, this becomes 1, so minus L to the power of 3. Does that make sense? So everything is multiplied here, then minus another 2 multiplicative. K to the power of 2 is going to become 1, if K is equal to 1.
And then K to the third goes to 1, and then it's negative 1, and then you distribute.
1 to the power of anything is 1. 1 times 1 times 1.
It's just got that negative.
Just once. Yes, it has two parts, that production function. So we have a form or a production function that we are going to define as the short run. So this is going to be the short run production function, right? This over here is going to be then, if you think about it, the long run production function, because you can change both capital and labor on this one, right? So you see how short run and long run works in the minds of economists. That's sort of the whole conceptualization of this. So once you have a production function, then you can start calculating things, right? So for example, what is the marginal product of labor? The marginal product of labor, you take a derivative of your Q function with respect to L. That's fantastic. So what did we have? We had 600 times L squared. So if you take a derivative with respect to L, it's going to be 2 times 600, right, times L for this particular derivative. And then you have L to the power of 3. So that derivative with respect to L is going to be 3 times L squared. Does that make sense? So this is going to be 1,200 times L minus 3 L to the power of 2. That is what we're going to call the marginal product of labor. So essentially, how do you use this function? At a specific level of L, you plug in the value of labor and you get what the marginal product of an additional unit of labor is going to be. So if you think that the marginal product of labor changes for different values of L, because it is a function of L, right? Can you calculate where the marginal product of labor is maximized? At which level of labor are you going to get the maximum marginal product? Each worker is going to be, or the worker is going to be producing the maximum output. So where, the question then is, where, and I'm going to stop on this question, where is Q maximized? Where Q is maximized, how do you do this? If you remember from your optimization methods, you set it equal to 0, right? So where is the effectively the marginal product of labor equal to 0, right? So we have an expression, 1200 L minus 3 times L squared. We set it equal to 0. That would be effectively 400 L is equal to L squared, right? Divided by 3. And if you solve that, you should get something like L is equal to 400 as the solution. One other thing that I'm going to do the calculation for and stop. What about the average product of labor? That's simply Q divided by L. That means that the average product of labor is going to be 600 L squared divided by L, right? That was our short-run production function, minus L to the power of 3 divided by L. So this should be 600 L minus L squared. That would be your average product of labor, right? This was your marginal product of labor. You can also make the same calculation, right? Where is the average product of labor maximum? You do the same thing, right? You equate the functional form of APL to 0. So you're going to have something like 600 L, minus 2L, or rather 600, right? Because that L goes away in the derivative. Minus 2L is equal to 0, which means that L is equal to 300. Okay? So an observation here, at this point of the average product, you haven't reached the maximum of the marginal product of labor, right? So you have a few ways to go before the marginal product of labor gets maximized. We're going to see how these equations play out diagrammatically when we come back on, not next Monday, on Wednesday.